Well, let's see. We have to find the linearization of f of x, which equals the square root of 1 plus x at x equals 3. So we're doing 1. We've got f of x equals the square root of 1 plus x at x equals 3. So let's collect some data. So f of 3 equals, well, if we replace x with 3, 1 plus x is 4, and the square root of 4 is 2. Now, let's find f prime of x. So f prime of x equals, and that's going to be 1 over 2 root of x plus 1, and then by the chain rule we take the derivative of x plus 1, but that's just 1. So now let's find f prime of 3. So f prime of 3 equals 1 over 2, and the square root, when we replace x with 3, we get square root of 4, and the square root of 4 is 2, so that's 2 times 2 in the denominator, which equals 1/4. Now we're ready to find the linearization of f of x at x equals 3. And we know this. The linearization of x equals, and for any constant a, f of a plus f prime of a times x minus a. Well, in this case, a is 3, so we have L of x equals f of 3. Well, f of 3 is 2 plus, and f prime of a, well, f prime of 3 is 1/4. 1/4 times x minus 3. So let's simplify that. And so we have 1/4 x minus, and 1/4 times 3 is 3/4, and we still have this plus 2. So we need a common denominator, so we'll multiply by 1 in the form of 4 over 4. And we have 1/4 x minus 3 over 4 plus 8 over 4, which equals 1/4 x minus 3 plus 8 is a plus 5 over 4, and that's our linearization of the function given at x equals 3. Well, for question 2, we have to find dy when y equals x to the 5th plus 37x. So first we'll find dy dx, which equals, by the power rule, 5x to the 4th plus, and the derivative of 37x is 37. Now, we'll multiply both sides by dx and dx. And now we've isolated dy. And that equals 5x to the 4th plus 37 dx. And we're done with that. Now for 3, the question is find the values of dy when x equals 1 and dx equals 0.2. So dy equals, and we'll replace x with 1. Well, 1 to the 4th is 1, so 5 times 1 is 5, plus 37, and in place of dx, we'll install a 0.2. So 5 plus 37 is 42, and that's times 0.2, Well, if we double 42, we get 84, but that we've multiplied by a 0.2, so we have to move that decimal over one place, and we get 8.4, and now we're done. Well, for our final problem, 4, we're given that the radius of a circle is 10 meters, and it's going to be expanded to a radius of 10.1 meters. So there's going to be a change in the radius, and that change is going to be dr equals 0.1 meters. And then we have to use the differential of the area to estimate the increase in the circle's area. So let's do that. And so area equals, of a circle, pi r squared. So dA dr equals 2 pi r, and multiplying both sides by dr, we have that the differential of A equals 2 pi r dr. Now, we are going to let dr equals 0.1, as we have here, and we're going to evaluate the differential of A for a radius of 10 meters, and that equals 2 pi, replacing r with 10, and dr with a tenth, 0.1. We have 2 times 10 is 20, 20 pi, and we still have this factor 0.1, and we'll move the decimal over 1, and we get 2 pi. And that's the estimate of the increase in the circle's area. So dA of 10 is an estimate for the increase in the circle's area when the radius has been changed from 10 meters to 10.1 meters. Now, let's use this to estimate the area of a circle of radius 10.1 meters. So area of circle of 10.1 meters equals approximately the area of a circle of 10 meters plus the differential of the area of a circle of 10 meters. So that equals, well, an area of a circle of 10 meters, squaring 10 we get 100, so that's going to be 100 pi, and plus the differential of, differential of A of 10 is 2 pi, and when adding these together we get 102 pi meters squared. Now, if you do a direct calculation installing 10.1 meters in for the radius and square 10.1 and multiply it times pi, you get 102.1 pi. Now, let's compare these two results, and you can see that our estimation was very close to the actual value of the area when the radius is 10.1 meters.